Hey and welcome. Today we're going to talk about something that's honestly one of the most powerful tools out there for thinking more clearly. It's called Bayes' Theorem. And really, it's just a simple way to update what you believe when you get new information. Trust me, once you get the hang of it, it can save you from some really common and sometimes pretty costly mental traps.
So to kick things off, let's just try a quick puzzle. Imagine you take a medical test, and this test is 99% accurate. You get the results back, and it's positive. So here's the question. What's the probability that you actually have the disease? Come on, what does your gut say? Probably something like 99%, or, at least pretty close to that, right?
Well, believe it or not, the actual answer when you have all the facts is just 16.67%. I know it's shocking, right? It feels totally wrong. How on earth can a test that's 99% accurate lead to a chance that's so incredibly low? Well, that paradox is exactly what we're going to unpack today.
So, how in the world do we get to that number? The key is realizing that the 99% accuracy number isn't the whole story, not even close. There are a couple of other crucial pieces of information that we're missing, and they completely change the entire picture. Okay, so here's the full scenario. First, this is a pretty rare disease. Only 1% of the entire population actually has it. Second, yes, the test is 99% accurate at spotting the disease if you have it. But third, and this part is the real game changer, the test has a 5% false positive rate. That means 5% of perfectly healthy people will get an incorrect positive result.
So there's our challenge. We've got these three different numbers, and we need a way to combine them logically. We need a system to update our belief from, well, there's a 1% chance I have it, to a real concrete probability now that we have this new piece of evidence, the positive test.
And the tool that lets us do this perfectly? You guessed it. It's Bayes' Theorem. Now, don't let the name scare you off. It's really just a formal, structured recipe for updating our probabilities whenever we get new info. At its heart, the theorem is all about this one simple idea: finding the probability of something, let's call it A, given that something else, B, has already happened. So for our puzzle, it's what's the probability we have the disease, given that we've already tested positive? It's really just a framework for updating what we know.
Now, this is what the theorem looks like as a formula. And I know, it might look a little intimidating with all the letters and the lines, but I promise each one of these little pieces has a really simple, intuitive meaning that we're going to break down right now. And this is where it all clicks. See that P of A? That's your prior. It's what you believed before you got any new evidence. P of B bar A? That just asks, how likely is this new evidence if my original belief is true? P of B on the bottom is simply asking, how likely is this evidence to happen, period? And the thing we're solving for, P of A bar B, is our posterior, our new updated belief. See, it's just a few simple concepts dressed up in math. Okay, enough theory. We have our confusing medical scenario, and we have our belief updating formula. It's time to actually plug in the numbers and solve this mystery once and for all. We're going to do this in 4 really simple steps. First, we'll nail down our prior belief. Second, we'll define the evidence. Third, we'll figure out the total probability of that evidence happening. And finally, we'll just plug it all into the formula. Let's do it. All right, step 1. What is our prior belief? This is just the chance of having the disease before you even walk in to take the test. We already know the disease rate for the general population is just 1%, or 0.01. That's our starting point. Step 2 is about the evidence. What's the new information we have? It's the positive test result. So we need to know the probability of getting a positive test assuming someone actually has the disease. We were told the test is 99% accurate in that scenario, so the probability is 0.99. Simple enough. Okay, now for the most important, and maybe the trickiest part, what's the overall chance of anyone testing positive? Well, think about it. This can happen in 2 different ways. You could have a true positive, that's the 1% of people with the disease times the 99% test accuracy. Or you can have a false positive, that's the 99% of healthy people times that 5% false positive rate. When we add those 2 possibilities together, we get a grand total of 0.0594. That's the P of B for our formula's denominator. And finally, we just put it all together. Step 4, we solve. On top, we multiply our prior belief, 0.01, by the likelihood of the evidence, 0.99. Then we divide that whole thing by the overall probability of a positive test that we just calculated, which was 0.0594. And boom, there it is. The math works out to about 0.1667 or 16.67%. So even with that positive result from a test that we're told is 99% accurate, there's still only about a 1 in 6 chance that you actually have the disease. It's crazy, but it's true.
So let's get to the big question. Why does our intuition get this so incredibly wrong? What did our gut feeling miss that this formula caught? Well, it all comes down to the power of that very first number we started with, the prior. The crucial point here is that the initial probability, the chance of having the disease to begin with, was incredibly low. Our brain just latches onto that big, shiny 99% accuracy number, but it completely ignores the much more important fact that almost nobody has the disease in the first place. This starting probability has a name. It's called the Bayes rate, and forgetting about it is such a common mental error that it has its own name too, Bayes rate neglect.
This table really just sums it all up perfectly. Our gut feeling zooms in on that 99% number and ignores everything else, especially how rare the disease is. It jumps to a conclusion. Bayesian thinking, on the other hand, forces us to start with the rarity, that 1% Bayes rate, and then carefully factor in all the evidence, both the true positives and the false positives, to arrive at a conclusion that is way more accurate and, actually correct.
And look, Bayes' theorem isn't just for weird medical puzzles. It's a way of thinking you can apply to almost anything, from a news headline you read to an investment to just an argument you have with a friend. It teaches us to start with what we know and then carefully, logically, update our beliefs as new evidence comes in. So the only question left is, what belief are you going to update next?